The traffic has gone by now, so I will show you this particular chunk of rock here, which is a gneiss. Fairly high-grade gneiss. You can see the banding in the rock, and it even looks as though it might have some gneiss characters. That what looks like it might be little eyes in it here and there. It's not a good gneiss, but it definitely is a gneiss. It's a high-grade metamorphic rock. Now, above it, hold on for a minute.
All right.
This goes by and I get another rock.
Okay.
Very convenient right here that I've got all
Looks like
these assorted rocks.
Greenstone?
How did you guess?
It's greenish.
It's green. I mean, I got a fresher piece here. Tough rock.
I think we need goggles.
Will probably help. The cocoon of a moth. Picked an odd place to put it. Well, we can see a little bit of fresh there. And you can see it's got a phyllite. So this has been metamorphosed under pressure. This is a meta basalt. And I think one of the times I was here with the class, my class, there was a class from Ohio here doing the same thing, geology class from Ohio. And they wanted to visit this particular spot because it is a classic occurrence. This rock is on the order of 800 million years old, and it's going to hold off until the car is back. Okay, there we go. And this was a basalt. It's been changed by heat and pressure. It's now a greenstone with some phyllite character to it. And it does have associated zircons in places, and so you can get the data. And it's a flood basalt. It is covered an enormous area, which is very typical of what happens when you start stretching an area apart, pulling it apart, and you get the release of pressure, and it causes melting. That's because this rock is related to the breakup of the supercontinent of Rodinia. Supercontinent of Rodinia. Nobody ever heard of it. Everybody knows Pangaea. Nobody knows Rodinia. But the other rock I had here, which went right here, this rock has zircons in it that are 1.1 billion years old. And it, in places, this isn't really a good granite gneiss. This isn't really very good granite. In places, it's a lot more like a good granite gneiss, but this is a part of the same. This is a part of the same rock. And the story of this rock is that it started out as a granite, which is the root of a volcanic mountain range, like Yosemite National Park today. There used to be volcanoes there. The volcanoes are gone. The rock has been raised. The shelf, the rock has been raised up there, and you've eroded away the mountains, and now you're looking at the granite batholiths that fed the volcanoes. Okay, that's where most granite comes from. Right after the granite was intruded into the batholiths, shortly after that, there was a subduction zone there with volcanoes. The land mass on the other side of the ocean crashed into where the subduction zone had been and changed the granite into a granite gneiss in making the supercontinent. The supercontinent, by the way, wasn't Africa that time. That time it was South America. And then 800 million years ago, it pulled apart again. Where do you suppose the other part of when it pulled apart? Where's the rest of it? Where'd it go?
South Africa?
South America.
Oh.
If you go to northern South America, to Colombia, to the Sierra Nevada de Santa Marta, which is 18 highest mountains on the Atlantic Ocean, 18,000 feet high. And you can stand up there and look down at the Caribbean beaches. It's an interesting place. Anyway, the core of that mountain range is Granite Gneiss, 1.1 billion years old. That's the stuff that was ripped off North America 800 million years ago when these lavas came out and flooded this whole area. Okay, there we go. We have the assembly of Rodinia in this rock, where the continents crashed together and made Rodinia. And in this rock, we have the record of the breakup of Rodinia, when a big chunk broke off and drifted south to become the northernmost part of South America. So now at least you've heard of two supercontinents. Those aren't how many supercontinents there were. Still fighting over that. The trouble is, the farther back you go, the worse the evidence becomes. For this particular set of rocks, for example, which is 1 billion years old, this has all been messed up because it lies pretty much along the same line that Pangaea was assembled. And when you assembled Pangaea, you messed up these rocks. If you want to go back and find a supercontinent, say 3 billion years old, and we have them, the evidence is even worse, because a lot of the rock has been lost to erosion or subduction, and most of it, what that remains, has been through one or two more supercontinent building periods. And that messed up the evidence even more. So Gondwana and Laurentia, the two chunks that formed Pangaea, we understand pretty well. Because that evidence hasn't been messed up. And we can still put the jigsaw puzzle together with Africa and South America and North America and Europe. It has been messed up a little bit, especially around Central America, because a fair bit has happened in that one particular area, and it makes it difficult to figure out the details of that area. But in general, the evidence is good. Rodinia, which is 500 million years earlier, it gets sticky. They're still fighting about what was on the west coast of North America at that time. They aren't quite sure. Some people say Antarctica, some people say Australia. We don't know, really. And if you go further back than that, it gets even harder. So, whatever I read on the older supercontinents, I take with a grain of salt. They may be right, but it's sticky. No, one little bit, I've looked at this contact right in this area in detail, and the picture I had before I came and looked was there was a nice clean boundary. After all, the rocks above 300 million years younger than the rocks below. 1100 million versus 800 million. And it should be a nice clean boundary. It isn't. It looks like they're interleaved, and they shouldn't be. interleaved. You shouldn't find a layer of granite gneiss, greenstone, granite gneiss, greenstone. And I think probably there's a master's thesis right there. I suspect what has happened is that in the Pangea collision, remember this whole thing is on an enormous anticline that was built during the Pangea collision when Africa collided. I suspect that what has happened in that is that the contact between the two, 800 million and 1100 million, were smeared out, and there was thrusting along the boundary, and little pieces of the lower one were thrust above little pieces of the upper one locally, just in places. That would take a fair bit of close investigation along the entire boundary between the two rocks, which I haven't done, and which I have neither the time nor the inclination to do. But I think somebody ought to do it, look at it, and investigate just to find what the details are here. Every time I've seen it mentioned, the assumption is that it's just a nice simple contact, a nice simple boundary, and it ain't. Okay, that's all I have to say here. Do we have any questions or comments on this particular one? As I say, it's a classic spot because there's a third of a billion years between the rocks up there and the rocks down here.
Is this one of your older rocks?
Very possibly. Very possibly. Yeah, I'm going to take these two along. These look like nice samples. And if this isn't a typical granite gneiss, all to the good. It's not as simple here as people say. It's more complicated than people say. It's not all plain, ordinary granite gneiss, but that is a very interesting rock in its own right. And actually, there is good granite gneiss in here too. But we have more rocks to look at.
Okay.